So let's start. Yes, so let's start. So today is the second lecture in quantum computing. Yes, and let me rehearse once again. Yes, let me rehearse with what we have finished previously. Yes, so we defined the state of multi-qubit system. Yes, and this is just the last slide of previous lecture. Yes. So that we have, this is a long vector, so it belongs to a linear high dimensional, exponentially large dimensional space with the notation of tensor product and with two conditions. Yes. And I recommend strongly ignore the second condition. Yes. And the first condition is written here, and I don't know why, but I forgot to say that if we look onto this as a linear space is Euclidean metric, and the condition one is just that the norm of this vector is equal to one. That's nothing more. Yes, so we are on a 2 to the power n minus 1 dimensional sphere. Yes, and also with this thing, so this is with this thing, it's certain projective space. Yes, but I would ignore during the course the fact that it is a projective space because I need a linear structure. I need to summate points, and you cannot summate points in projection space. Yes, so that's yes. Okay. So now the model consists of three things: quantum bit, quantum gate, and measurement. Now let us come to quantum gate, which is an operations which we are allowed to do. And here I would like to make some motivation from quantum mechanics. Even that in the end I would, as I promised, give just a mathematical model. Here it is very easy to demonstrate why the model is as it is. All right. So all of us have heard about Schrödinger equation. And I just screenshotted the Schrödinger equation from the Wikipedia. Yes, so and in that case, psi, yes, so Wikipedia use capital psi, but I use small psi, yes, is a state of a quantum system. Yes, and H here is something which they call an energy operator. Yes, and by quantum mechanics, energy operator is a linear self-adjoint operator. So I kind of don't motivate this. I just say it is linear self-adjoint operator. Yes. And I recall what is the self-adjoint operator. So the scalar in scalar product, you can just move on another side, or it is the same as that on diagonal you have real. If you represent it in some basis, yes, on a diagonal it is real values and values which are symmetric, diagonal symmetric, then they are conjugate. Yes. So then let us look carefully at this. This is a linear differential equation. Yes, even that it is super high dimensional, but this is still linear. So it can be solved via notation of exponent of matrices. And here what we have in the exponent, we have 1 over Planck constant. We have I, yes, which comes from here, yes, which have this self-adjoint operator, and we have time, yes. And this guy is real, time is real, yes, minus is also real. So we have something purely imaginary multiplied by self-adjoint operator. I mean, it might be not so obvious, but this is a mathematical statement that exponent of I times self-adjoint operator is a unitary operator. Yes. And unitary, next slide, I will give a lot of properties. Yes. Yes, so which is something of absolute value 1, yes, but this is operator version of this, yes. Good, thank you, yes. So, and because of this, it seems that whatever I do with a quantum state, I can only apply unitary operator to it, only linear, unitary. So all the operations which I do are unitary, linear, and this would be my postulate. So it came from quantum mechanics, but mathematically I can just postulate the fact that it is like this. Yes, and this is the way that how quantum computers works. And this is kind of fundamental restriction of quantum device. Yes, yes. Yeah, H hat and H here is the same because this I just copied from Wikipedia and this I type it by myself. And here it's also Planck constant that I wrote H here, yes, and Desculpa, yes. Sorry, yes. So professor is lazy. And we don't know exactly what would be the construction of quantum computer, yes? But in any case, whatever is the quantum computer, it would allow us only operations of this type. This is because of physics. This is a super fundamental restriction. So, okay, now, how to say, later in the course, not today lecture, but at some moment, I will discuss what concrete operations can do real computers, yes, which exist. And this could change from model to model, yes, but none of them would overcome this restriction. So, okay, let me mention few important properties of unitary operators, yes, that, okay, it would appear in the course, might be some other would appear, but this is what I think is important to mention right now. First of all, they preserve norm. So at the moment when I told that I use only unitary operations, if I start with a quantum state, so with a vector of length 1, I will always automatically stay in this. So this is not a condition that I go from quantum state to quantum state. This happens automatically. Yeah, so this postulate keeps me inside the correct statement of the things. Another thing, okay, I would put two together, I guess, that it maps orthogonal vectors to orthogonal vectors. And this is a special importance because it means that it maps basis to a basis, yes. And in general, it also preserves angles, yes, because it preserves scalar product. Yes. Yeah, preserves scalar product, preserves norm, I mean, that's it. And what is crucial for today's lecture, I mean, this is just, I mean, important, we will use it later in the course a lot, but for understanding of model, this is, okay, the first one is important. But for today, it is important, the last one, that it is reversible, that all the calculations are reversible. So for any unitary operator, there is its inverse. Yes? So whatever you calculate forward, you theoretically can calculate backward. Yes, and this is a very strong restriction. Yes, also inverse is a conjugation of the operator. Yes, but I mean this is property. This is not what's important now. And the fact that everything is reversible is a very strong restriction, because this would kind of, as I use this philosophy, bless and curse. Yes, I will show today what is the bless of the model. That with this situation, you can have a huge parallelism. Yes, we will see this today later. But there is a curse for this. Yes, there is a negative side, that all the calculations are reversible. And in particular, yes, if we come to classic computer, yes, so we have an operation AND, yes, which maps xy, where x and y are 8, 0, 1, yes, to x and y, yes. This operation is not reversible, yes, because, okay, I calculated the map, and there are two similar values for different inputs. So this means that we cannot use AND in quantum computers. So there is no analog of this. And there is no analog of OR, and there are other things. And a lot of things which we get used in classical computers, we cannot do. So we will need to find a way around or to do something. Yes, so there would be a way how to calculate analog of AND, yes, but in that case we need to introduce an extra qubit. Yes, so which would be ancilla qubit. This is not for today. Today we remember that this is a huge restriction. So it's not correct that classical computer is automatically embedded in the quantum computer. Yes, so that's. So we will see how it is embedded, but we need to work for it. Yes, it's not happening automatically. Yes, and what is the quantum program? I mean, it's boring, it's sequence of quantum operation. Yes, and we start with a certain state, and we will always assume that we start with state of zeros. This is, and because we need to start with the same, and when you turn on your classical computer, yes, also your memory is, everything is zero. Yes, so that's like this. And this is here string notation. I just demonstrate the notation, which I will use a lot. So in most of the cases, I will not write a program on a blackboard. I will draw a picture like this. Let me explain. Each line is a qubit. Yes. So if I have n qubits, I have n horizontal lines. And each block is an operation which I apply to it. And you can, it would usually have names, yes, and something like this. And you see it intersects not all the qubits. Yes? It means that operation is applied to only a finite number of qubits, not to all of them. This means that on all others, it is identity. Yes, so I mean, not everything at one moment. Yes, so later I will show how formally mathematically to write this, how to calculate this if you do not on all of them. Yes, and the program works like this. We start from zero, we apply first operation, we apply second operation, blah, 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 blah. And in the end, I mean, we still apply, yes, we don't get information. In the end, we measure, yes, we read information. And the read corresponds to the part measurement. And this would be the most different part from classical computers. Because up to now, I do not go far beyond classical computers. I mean, I still in the same philosophy. Yes? So I have a state, I can apply some operation to it. Okay, it happens that this is linear, it happens that it is reversible, but I mean, this is still the same idea. But the measurement would be different. Yes, I put here the measurement in the end. It's not necessary in the end. You can combine it in the middle, but for simplicity, now let us think. And if you do calculations, it goes from 0 to U1, 0, from U2, U1, 0, UK minus 1, U2, U1, 0. And this is the way how I will write this, because this not only explanation of notions, but also explanation of notation. Yeah, so this is...
Professor.
Yeah.
Just a question. You said just now that we can also, for instance, measure in the middle of a given set of operations, then we perform another set of operations. But by measuring during the execution of the program, don't we kind of break the superposition of this state? So if we have...
That's correct. It will change the state. There is a theorem that for any program with a measurement in between, you can write an equivalent program with measurements in the end.
Oh, okay.
So there is such a theorem, yes.
Okay.
But I mean, when we go to the details, yes, I will show that theorem exists, but there are some details, yes. So there are
Okay.
some moments which can push you actually to do measurement, not in the end, but in the middle, yes. So
Okay.
there are some reasons, could be some reasons, yes. But up to now, we are just introducing the moment, yes, not everything at the same time. Yes?
Okay, great. Thanks.
So, and operation is called quantum gate. This is just the name, and this is why computers are called gate-based quantum computers. Yes, so this is the way how it works. Okay, so I have. So what we should do? Yes, in that case. Yes. So I told that we have a scheme. So we need to construct. It's called a scheme. Program is called quantum scheme. So we need to write a scheme. Yes, and it typically consists of two steps. Yes, we need to find kind of on a paper. Yes, so in our brains, operator U which would solve our goals. I mean, we write program for something, yes, to achieve something. So we need to find a unitary operator which would help us. And after this, there is a second part to which would be mostly devoted this course, is that we need to represent this unitary operator of a huge dimensional space as a composition of operators which are implemented on a physical computer. Yes, because there are some restrictions. Yes, so what? In most of the cases, I mean, at least IBM, Google, yes, they implement such set of basic operations which allows you to create any unitary operation as a composition of them. Yeah, so there is, I mean, it's not finite, but I mean, finite families of operators which allow to do this. And usually it is done, but we will see how actually it works. Yes, so because here there is a devil in detail, because we want to have a program to be fast. We want it to be better than classical computer. So this sequence has to be short. Yes, the theorem that everything can be decomposed into a product is not enough. Yes, they need to look what can be decomposed in a short sequences. Yes, and in most of the cases, yes, so that most of computers have a lot of one-qubit operations. Yes, and this is always constructed in a way that, I mean, it's easy to create any one-qubit operation. Usually they have very few two-qubit operations, because actually one operation is enough. I mean, not any two-qubit operation, but there are operations which are enough to construct all two-qubit operations, and together this operation with all one-qubit operation gives you the full set of things. But here there is a certain devil in detail. Yes, that one-qubit operations now are implemented relatively precise. Yes, so that they have 0.9999. I don't remember how many nines. Yes, precision. But the two-qubit operations, this is still a problem. Yes, so I would say that they work usually with a precision 0.98, 0.99, which could be say, oh, it is almost one. Yes, but if you have 100 of such operations, then you get an error comparable with the whole program. Yes, and be sure that in almost all situations you will need more than 100 of such operations. There would be one important 3-qubit gate, which most of the systems allows you to put on a scheme. Yes, so make it to write it as a 3-qubit. In some cases, it is implemented as a composition of 2-qubit and 1-qubit gates. And actually, I don't know, does they have a good, just physical implementation? Yes, but it would be there is one very important 3-qubit gate. Because of this, I mean, companies pays attention. And mathematically, what means that we apply to 3 qubits, yes, some gate. Let us assume that we apply to first 3 qubits. This means that for the whole set of qubits, we apply operator for the first 3. We have this and tensor product time identity on others. So this is a linear operator. So next slides, I will show how to practically calculate this. Because of course, we are not going to write matrix of the size 2 to the power n to 2 to the power n. And if you want to apply it not to first, second, third, but I mean any other set of qubits, you just need first to make a permutation of qubits, apply this operator, and make permutation back. Yes, and so how we will calculate? So because, and this would be today, so the main idea how to calculate the values of result of work of the program. I told that it's nonsense, try to write a matrix 2 to the power n times 2 to the power m, yes, even for n equal to 4. You will make more mistakes in writing number of columns, yes. So the normal approach is the following. So it's enough to know how, so each vector we can write in a linear composition, yes, of basis vectors. And because U is a linear operator, it's enough to know how it acts on a basis vectors. And on a basis vectors, each of basis vectors is just sequence of 0 and 1. So you can pick up those to which operation works, keep the rest the same as it were, and apply it only here. And kind of if it was 2-qubit operation, that, I mean, this would be matrix 4 by 4. Yes? And 4 by 4 is already a reasonable size. Yes? So this is, that's the strategy. Yes, let us do some calculations. Yes, first we start with 1-qubit. Yes? So assume that we have a unitary matrix, A, B, C, D, because it's unitary, not arbitrary numbers, A, B, C, D are possible, but for the calculation, it doesn't matter. Yes. So how it works? Yes, A, B, C, D. Yes? So remember, 0 is 1, 0, 1, 0, 1. Then you can multiply this vector, this matrix of the vector, get a vector, recall the composition of it in a sum of vectors. Yes, so we get it for 0, we get it for 1. We are good boys. Yes. Now let us see how it would act on a superposition to basis state. And this is the notation which I use. Yes, so I will write error and U operation which I apply on top of it. Yes, so this is how it works. And okay, I just put coefficient X here. I write the image of 0 after this, and the same with y and image of 1. I open brackets, I regroup. Yes, so same as I do with linear spaces. Yes, so this is a good idea. So you do this as a formalism. And I actually recommend to look on this as on formalism, at least in the beginning. Yes, at some moment you get, inspiration from the quantum mechanics, and you will start to see which vectors should be preserved, and so on. But you can start with a formalism. Yes. And okay, indeed, if we just multiply A, B, C, D on a vector, we will get the same. Yes, I mean, this is natural. Yes, and moreover, if X and Y had the norm 1, this also always will have norm 1 if U was unitary. Yes, so A, B, C, D cannot be everything. Yes. So concrete example. Yes, without X, Y, A, B, C, D. So this is gate H, Hadamard gate. It would be very important in the course. It would appear constantly, and this is defined by such a matrix. Basically, it sends 0 to sum of 0 and 1, and 1 to difference of 0 and 1. Yes? Okay, with a proper coefficient because we need to keep vectors unitary. Yes, you can check that that those vectors are orthogonal. Yes, so this is important. Yes, so you cannot get here not orthogonal vectors. What? No, it's not a rotation. Or it is, might be, because on the plane everything is rotated.
But yeah, because once here you are at 0, then you come here. Here.
Might be, yeah, might be because this is. It doesn't matter. Yes. So because here it is much more important that it moves any state actually to half sum or half difference. Yes. Kind of this is the way to produce probability 1/2 in the end. Yes. So, but we don't know this yet. So let us calculate something. Yes. Let us consider such a vector. Yes. I put here arbitrary coefficients, yes, but in such way that sum of their squares is equal to 1, yes. And okay, I apply h, yes, and I keep here square root of 3 divided by 2. I multiply it on image 0, yes, and oops, here should be 1/2, yes, so that's 1. Yes, so but the result is correct. Yes, this is the misprints. Yes, so never use a copy and paste. Yes, in software development they teach us. Yes, so that's in preparation of presentations as well. Yes, and in that case, okay, you look on the coefficient here. This is square root of 6 divided by 4. Yes, and if you put here 1/2, it would be square root of 2 divided by 4. So get those values, and you see here there is a plus, here there is a minus, or square root of 6. Yes, keep with the same sign, and minus square root of 2, plus minus square root of 2 is with different signs. Yes, so this is what could happen, and what is happening, and what we will use a lot in the actual course. Let us now calculate for 2 qubits. Yes. So now let me come back to A, B, C, D. Yes. Once again, and let me consider not the full vector psi. Yes. But vector with 0, 0 plus 0, 1. Just 2 elements. And let me first calculate image of U under the first, applied to the first qubit. And after this calculated, U applied to a second qubit. Yes, so if we apply to the first qubit, and I will write it like this, U tensor identity. Yes, then what I should do? Yes, I put here X, I replace the first zero by U0, and the second zero keep 0. So here I keep Y, I replace the first zero by U0, and put 1, keep the second qubit as it is, and after this I substitute, yes, and open brackets and open in a normal sense. Yes, and here we see that this would be a certain sum of, and here I also change XA, AX. Yes, so it would be sum of all 4 possible bases. Yes.
So, when we represent the action as the product, we assume that these qubits are independent.
This is the feature. Like, let me explain. This is the feature. So original state psi, the qubits might be not independent. Yes, but action is linear. You can write it as a basis states, and inside each basis state,
They are
they're independent. This is, but this is kind of idea of a tensor product. Every vector in tensor product you can represent as a sum of vectors which are direct products. Yes, so I mean in a fancy language. Yes, so but yes, this is the idea. This is the problem, that original state is not necessary. For original state, they are not necessary independent. Yes, but you still need to calculate this direct product. Yes, so but you decompose it into basis states, which are now direct products, and you apply it to each of them, and after this you calculate the sum. Yes, yes, yes. For this method of calculation, this is necessary. Yes, in theory you can choose arbitrary basis. Yes, but if you choose basis in which the basis vectors are not direct products, yes, so I prefer to use direct product, not independent. Yes, because this is not completely like random variable. Yes, and now let us go for the second. Yes, let us calculate it for the second. Yes, ID times U. In that case, we keep the first vector. We should change the second. Yes, and we do substitution. We insert, and okay, now not all of the states are represented. Not all of the 4 states present. Kind of, it is. I mean, it is important. Do you apply it to the first qubit or do you apply it to the second? I mean, this is obvious, but this is a demonstration. Okay, let us calculate for a certain concrete. Yes, and let us calculate. On the blackboard, might be you can tell me how to do this. I apply to the first qubit. Someone, please help me. What? Oh, 1 over square root of 2. Yes, yes, yes.
Yeah, 0, 0 should 0. Tensor product 0. That does apply H first.
1 over square root of 2, H of 0, and okay, tensor 0. Yes.
plus 1 over square root of 2, h of 1 is 1,
Okay.
and then h like 0 is 1, 1.
This coefficient 1 over square root of 2. 0 plus 1.
Yes.
Tensor 0. Yes. One over square root of 2 or 0 minus 1. Yes, tensor 1. Yes, and now it's the time to open brackets. Yes, and this would be 1/2 0 plus 1 0 plus 1/2 0 minus 1 1. Yes, which is 1/2 of 0 0 plus 0 1 plus 1 0 minus 1 1. And I would say the following. There is a room to make a mistake, calculation mistake. So you need, how to say, somehow to adapt yourself, yes? Because, I mean, this is a lot of calculation, yes? Even for such a simple story. And one of the things which I recommend to self-control, yes, not to make mistakes, is in the end to look, do you get the vector of length of norm 1? Yes, because, okay, here all of the components were different, yes, but usually you will summate some of them, yes, but sometimes you need to summate, sometimes you need to put minus between them, they would be with different coefficients, yes, so there is a room for mistake, yes. And if you make this mistake, I mean, 90% probability that you will not get a vector of length 1. And if you know that there is a mistake, I mean, it's much easier to find. Yes. So that's the story. And now I would do one more abstract calculation to show how it works for n-qubit system. Yes, and because it is for n-qubit system, it would be something not very concrete. And actually, the main purpose of this story is to show how, I mean, application of 1 qubit gate. So I will still apply H. Yes, so that's H, yes, which is 1, 1, 1, minus 1. Yes, so one of the actually simplest gates which exist. And show what computational complexity it creates. Yeah, so first, before I start to apply, yeah, so n-qubit state I write in a such form. Yes, I would like to separate the first qubit from the rest story. Yes, and in that case I consider divide k into two groups. Yes, less than 2 to the power n minus 1 and bigger than 2 to the power n minus 1. Yes, and the first corresponds to 0 k, but on n minus 1 qubit, and the second corresponds to 1k to n minus 1 qubit. And in that case, now I want to apply H identity, and now it is represented in a form such that I can apply H to the first qubit in each term. Yes, so there is no, obviously, need to further decomposition. Yes, and this is what would happen. Yes, so I replace 0 by half sum, not half sum, 1 over square root of sum 0 and 1. And here, pay attention to the coefficient. Yes, and 1 I replace by 1 over square root of the difference. And now, I mean, yes, I need to open the brackets. I put 1 over square root of 2 here, yeah. And now I observe that in both parts, I have terms 0k, and in both parts, I have terms 1k. And I group them. Yes, and this is not only I do on a blackboard, on a presentation, but also quantum computer do in physics. Yes. So it creates a state of such form. 1 over square root of 2 is in front. And in front of 0k, I have certain sum. And okay, here is a misprint, yes. And in front of 1k, I have certain difference. Yes, and so this is the result. And okay, this is a state which I can represent just in the form with coefficient. Yes, I call them B, yes, with indexes. And I know that bk is equal to 1 over square root of 2 sums, and the other b is equal to 1 over square root of 2 differences. And in one operation, we made all these calculations. And imagine that n is equal to 100, and this is 2 to the power of 100 calculations in one cycle of computer. Yes, so in one time element. Yes, so this is what we would have. And this is a huge parallelism. Yes, and this is actually such type of things, yes, is the way how we get a profit from quantum. Okay, there is quantum memory, yes, but for calculation, this is the profit, yes. And here I use just one qubit in a simple state, and this is among the existing calculating devices. This is the most similar to GPU, yes, which can also do some simple operations, but in parallel. Yes, it can easily summate two arrays. Yes, and this is kind of the same. I summate two arrays. Yes, but here I have a better parallelism. Yes, I have a potentially more simultaneous operations. But at the same time, I'm still restricted by this unitarity rule. Yes, so if I calculate somewhere sums, I should calculate somewhere differences. Yes, so yeah.
About this parallelism, so how the computation of time depends on the number of these. Yeah.
It doesn't depend.
So you can take millions.
Yes. 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 Yeah. So physically, how it physically works? You just yeah. So in any case, yes, how it works on a basic of physics. For this, we need to come to the very first slide. Yes? When I wrote a Schrödinger equation. Yeah. Let me come. Yes. So that's no, it was before. So this is the Schrödinger equation. So you physically create certain H. Yes, you create the an energy potential. Yes, you create your force. Yes, basically, and after this you run it for a time. Yes, and the time for which you run doesn't depend on number of qubits. Yes, and you put H to the and if you put your physical, like qubits are physical items. Yes, so it's not a good idea to say they are located. Yes, because in physics, located is in quantum physics located, but there are physical objects, and you kind of use your device to create, put laser or whatever, yes, to this particular one. You even don't know how many others.
Yes. So, but because you're always thinking of the one.
Yes, I how to say, I interact only with one. The rest is because of this entanglement, quantum physics. Yes, so this is not because of you. This is because of Schrödinger or who created all of this. Yes. Yes, they have to change their,
Ah,
and this is the critical step. Yes, let us better ask more questions than less questions. Yes, because this is exactly the magic. This is why, I mean, so there was a like Trudeau, yes, who made a famous speech, yes, as a prime minister, he told something reasonable about quantum computers. I mean, something not self-contradictory, 1 minute speech, which have finished. This is why we are so excited about quantum computers. But actually, he told them actually, we are excited by it not because of that. We are excited because of this. Yes, because we just interact with one qubit, and all other qubits made this calculation. Yes, and because of this, the time doesn't depend. I mean, it could potentially depend because I mean you have a bigger device, so you need to have a better precision, or I mean to move your laser to a longer time. I don't know, but this is already on the level of physical implementation. It is still, I mean, it is still one operation. Yes, and so summarizing, yes, so very small summary, yes. So we have a bless of exponential memory, bless of exponential parallelism, and the curse which we get that calculations are reversible. That we do not have and, we do not have or, we do not have a lot of other things which we get used to. Yes, I don't mention it up to now, but the main thing we cannot copy. Yes, so I put here my presentation. Yes, I copy it from a flash card. Yes, so it is still on flash card. This is also on computer. Yes, because of reversibility, you cannot do like this. Because if you put something on some place, what was there should be moved somewhere else. Yes, so the information about this should be still in the system. Yes. So that's. But by the way, I was always so in fiction movies you have usually teleportation. Yes, so when you go inside the super box and you appear somewhere else, but you not create your copy, you move yourself. Yes, so it doesn't. If there was an empty space and that empty space moved to this box, yes, kind of you swept with empty space. It doesn't contradict reversibility. Yes. Cloning contradicts. Teleportation doesn't contradict. Yes. So that's it with the quantum gates. So that's Sergey had very good duvida. Yes, a very good question about. I mean, does the time of execution depends on a number of qubits? Maybe there are more questions. Yes, so I just it was really very good. I should stress myself attention.
Sergey,
Yeah.
so just want to confirm because I found that discussion that you just made very interesting. So were you saying that physically speaking, what that equation you showed meant was that you only need to apply the force to those qubits and you applied all of them at the same time? Is this the correct understanding?
No. You should apply force only to one qubit, and you do not touch other qubits. And you need to very correctly choose the time during which you apply this force.
Mm-hmm.
Yes, so this is, and you don't touch other qubits. So you touch only one qubit. And the rest calculations is done by quantum mechanics, not by your action.
I see. I see. So it's kind of like a chain of consequences from your action.
Yes, this is chain of consequence. Yes, this is because they were somehow connected. Yes, so when you change one of them, you change all others. Again, not all, but I mean, okay, all. In this case, even all. You change others as well. Yes.
I see. That's very interesting. All
Yes,
right,
yes,
thanks.
but this, I mean, okay, I'm here in a course designed for mathematicians, yes? So we need better to understand what is the nature of quantum speedup, yes? And this is the simplest nature of quantum speedup. It's a hard story. Here is the remark. Assume that you had independent qubits. Yes, then, okay, you still formally have this summation inside, but it's not very interesting, yes, because if they're independent, each AK is a certain product, yes, and you would just, change the first element in those products. So one of the jobs which we would have to do, and which would be a hard job, and which is a hard job for physical implementation, yes, is not application of such H, is to really able to create such a big set of qubits where AK would be really independent, where this cannot be just by smarter software developer calculated, faster. Yes, that this is just really all of those summations are really different operations. Yes, cannot be deduced to one of them. Yes, so this is the story. Okay, let's come to measurements. And this is the most different part, even that among the three-part state of qubits, quantum gates and measurements would be the shortest. This is the most different, and because of this, I expect the most difficult. So please don't shy to ask if if you have some uncertainties. Yes. So the main problem in quantum computing is the following. So we have a state, and might be it contains the wonderful numbers which answers to all the questions in the life. Yes, for us. There is no way to know the values AK. There is no way to measure the value AK. Yes, and this reflects to, there are famous principles from quantum mechanics which aims to outside of the physics. Yes, there is no way to know the location and impulse of a particle. It's not very well applicable to concretely this situation, but this is the same philosophy. But what is more important, when we measure quantum system, we change it. Yes, this is less famous, but much more relevant to this situation. So we cannot know what is there, anything from the system without changing it. So there is no way just to read AK. Yes, whatever you do, you change the state. Yes, but as before, I would here I would not even refer to ideas like Schrödinger equation. I would just postulate certain behavior. Yes, and this would be the last element of the model. As usual, let us start with one qubit. So I think that we have a qubit which is in such state. Now I postulate what means to make its measurement. And it is the following. So this probability, absolute value of A squared, I get result 0, and psi would be forced to become 0. Yes, and this happens with probability A squared. And with probability B squared, I will read 1, yes, and read here means I read to my classical world, yes, to outside of quantum computer. So, like in a typical situation, you should have a quantum computer and normal computer nearby. So now you get this 0 in your classical computer and can use whatever you want to do in a classical. Yes, but at the same time, your state becomes 0. And this is the basic operation of measurement. Two things, yes. So it is probabilistic. There is no way just to say what would be the result. Yeah, so you have to enter the wonderful world of probability. But please don't be afraid. Yes, so this still all the probabilities which appears here is on the level of Dyson rolls of cubic here. So here, cubic is roll. Yes, just Dyson. Yeah, so there would be no, I don't know, sigma algebras or whatever. Yes, you should multiply, summate. Yes. So. And the second thing is that it changes the state. Yeah, so that you go in some superposition, and after this you become in a base state. Necessary. You don't know which of them, but you know that it would be either 0 or 1. Yes, no superposition, no fancy quantum state. Yes, and in particular, we can say something for sure. Yeah, so if we do two measurements consequently, we always will get the same result, yes, which is something natural. Yes, like if you think about classical system. Yes, so if you measure 2 times, you get the same result, and here it is true. Yes, even that you don't know this result, it is still the same. Yes, so that's, I mean, you still can, you know, prove some statements. Yes. What we do, so, okay, this was 1 qubit, yes, and that's it with 1 qubit, I mean, just 1 slide. And multiple qubits. Yes, so this is a big state. Yes, and we still, I assume that I measure the first one. Assume for a second, on the next slide, I will show how to do this, and we actually kind of such calculations did when we consider parallelism, but assume that it is represented in a such form. So this is A0 times some state here it should be index n minus 1. Yes, so that's n minus 1 qubits plus B1 also some state of n minus 1 qubits. Assume that we can represent it in such form. Yes, the hint it is always possible. Yes, but let us consider such representation. Then I postulate what is the output. Yes, with probability a squared, I got 0, and state of the system becomes 0 tensor product psi 0, so the first term. Yes, with probability b squared, I get 1, and psi becomes 1 tensor product psi 1. Yes. In all the cases, what is important, so it's very similar to previous case, but in any case, now kind of the state is a direct product of two states. You don't know what would be in the first term. Would it be 0 or would it be 1? But in any case, it's a direct product. And it is philosophically really like this kind of when you measure a part of a system, yes, or whatever this means, you kind of separate it from the other part of the system. Yes? And of now they are independent after measure. Yes, and this is what is important to know. And yeah. And once again, if we okay, if we measure not first qubit, we should just make reordering, yes, of qubits to see the result. And once again, if you 2 times measure the first qubit, you will get the same result, always. How I can represent in such form? I mean, I already did this. This is a formula from the calculation, yes, and kind of here I have a 0 times direct product, yes, and here I have 0 times direct product. The only tiny detail, so if I immediately write this as a direct product, here it would not be a quantum state because sum of AK squared for the half of them is not 1. So I need to normalize. And this is how I do this. Yes, so I just write it in such form. Yes, so as a psi 0, I take the first half of the sum. As a psi 1, I take the second part of the sum. And they need to have a coefficients. in front of them. And this is, I did my homework. Yes, so this, oh, it should be, here should be squares and should be modulus. Yes. Yes, I would, after the class, yes, I usually make corrections in the presentation only after this upload to the website and to the group. This is why I don't upload it before, yes, because it's unavoidable that during the presentation you don't observe some mistakes. Yes, and by the way, all of this means that when I do, and A is the probability, A squared becomes a probability. This means that when I do measurement, something somewhere do those calculations. And I mean, this is a sum of squares. I mean, this is a complicated story. Moreover, so in the first half of the course, yes, I would mostly use parallelism, yes, in a sense which I showed for quantum gates. But there would be a moment when I present how I can solve linear equations. Yes, and there I will use the driving force would be this part. So that's somewhere inside the calculated such quantities. Yes, and this would be the driver for solution of the system. Yes, for quick solution of this. Yes, it's also exponential sum. Yes, so that's possible. Yes, okay, so measurements has one calculations. Oops. Yes, I already told that when I say get result 0 or get result 1, yes, it means that I put those values in the classical wall. Yes, that I can use them, I can copy them, I can put them inside if operator, I can do whatever I want to do, but with classical. Yes, so kind of, it is always, there is a quantum part of calculating system and classical part of the calculating system. And by the way, so this is a philosophical story. So quantum computers are developing, yes, story. And in particular, there are languages and I don't know, theory of languages for quantum computers. So there was a part of a history that someone developed a language for quantum computer, and somewhere later proved a physical theorem that such there is no device which could implement this language. And so, I mean, this is an active story, yes. But in any calculation system, in most of the algorithms, which you will see, there would be two parts: classical calculations and quantum calculations. And there would be certain, communication between them. Yes, so classical will choose which gate you apply to quantum. You will read from quantum, and depending on this, I mean, do something. Yes, and I didn't find a good, language, good theory which describes the communication between them. And this is actually what I like. I'm happy with my course, yes, but there are parts which I would like to improve. And then this is this part, yes, because up to now, all my phrases about communication between quantum and classical, they do not have, operators inside. I just say this, yes. And I would prefer to have a theory, yes, and I didn't find anywhere such a theory. So, by the way, I'm old, you are young, yes, so sometimes you are better with information search. Don't be shy, to share with me if you find. Let's practice. Yes, I think it's always a good idea, practice. So we have this state. Yes, what would be the result of measurement? So this is basically answer to the question, how would look like tutorial sessions? Yes, so they are incorporated lectures. Yes. So how we will do this. Yes, I have a state, and I also will familiarize ourselves with the notation which I use. Yes? So don't worry, beginning of the course should look like quite slow motion. Yes, and this is on purpose. Yes, so at some moment you will feel opposite. Yes, so we do measurement. Yeah, what would be the result? We get 0, and state becomes 0. Let us remember that the result of measurement, if two elements, kind of 3 elements, with which probability, which value we got, and in which state will be the system, because there is a future. Yeah, so we need to know this state. Yes, and in that case, the second is probability 1/2. We get 1 and state 1. Yes. Okay, the second. Yes, so now I will not copy the state. Yes, so what is the second? Probability 3/4. So we get 0 in state 0. Probability, okay, 1/4. I believe that you can summate to 1. Yes. We get 1 and get 0. Don't forget to put square. Yes. The third. So now I put I here. So this has imaginary numbers inside. What? So the same as the first one. So the measurement give of the first and the third is the same, even that they are not equivalent. Yes, but the measurement is the same. Okay. We practice this 1 qubit. What is about 2 qubits? Yes. So because kind of here it starts like this is exactly when I want to pay attention to which state they can, because here it is trivial. Yes, 0 always 0, 1 always 1. Yes, this teacher is Shatu. Yes, so I don't know the good English word for this. Yes, so but now, okay, let me consider. Yes, so I have 0, 0 plus 1, 1, and 1/square root of them. Yes. So what would be, so how to calculate the result of measurement? Let us, okay, here I did like on the 5th and 6th, yes, I wrote which qubit. Here I didn't wrote, it is my mistake because actually the answer would be the same. Yes, but let us measure the first qubit. So this is my mistake. It's I know I can calculate in my memory that the output is the same. Yes, it's correct that I need to set up which qubit I measure. So assume that I measure the first qubit. So I first need to represent it in this special form. Yes, how I can do this? Where there was a 0 times something plus 1 times something. Yes. Here it is already in this form. Yes. I write it in a such, yes. And so, okay, let us write what would be the result of measurement. First of all, with which probability and what would be the result? Thank you. Yes, probability 1/2 out 0, state 0, 0. Yes. Yeah, probability, okay, 1/2. Yes, the output 1, right? 1, 1. What? Because this is 1, it is multiplied by 1. Yes, so I mean, this is, yeah, the story.
Change. You know,
Yes, so look, this is psi 0, and this is psi 1. And here I got 0 psi 0, and here I got 1 psi 1. Yes, and so I recommend the book Williams. And in the book Williams, after each chapter, yes, they have a lot of exercises. Yes, I mean, and they are of these levels. Yes, and I very recommend to everybody did those exercises, because I mean, you see that now. Okay, I wrote 0, 0, 1, 1. I mean, immediately. Yes, the result. Yes, but this is how to say. There should be practice. Yes, I mean, there is no more theory than I told. Yes, there is no secret theory. Yes, but a lot of calculations you can, see faster. And I believe that actually all of us will develop their own way, yes, to do this. So let us look on the Python. Yes, and now we have somewhere pluses, somewhere minuses. Yes, so because of this, the answer becomes a bit more tricky. Yes, so here it was obvious. I just copied part of the state. Yes, and all the elements before. Yes, and here, I mean, how to say, the result would be really kind of different. Yes, so that's from original state. Yes. So let us see how we will do the fifth. Yes. Well, let us do this. Yes, so okay, we have here, we look on the elements which has the first 0. Yes, and we got so 1/2, 0, 0 plus 1. Yes. And 1/2 plus 1/2, 1 times 0 minus 1. Yes. Now, what is the result of the measurement? Oh, sure. Thank you. Better? So that's, I create in a template. Yes, and okay, I even can say that somewhere the output would be 0, somewhere output would be 1. Yes, but which probability and which state is the output is still empty. So what are your feelings? First of all, is this a presentation which I showed on the previous slide. What is the value of psi 0? So the psi 0, yes, you think is 0 plus 1. The truth situation is not. Then you need to modify this somehow. Who see why it cannot be? Yes, it's not a quantum state. So in that case, we need to put here 1 over square root of 2, and we divide this 1 over square root of 2 into 2 parts. Yes? And now, this is my psi 0, and this is my A. Yes, and the same here. So I write here 1 over square root of 2, 1 over square root of 2. And this is my psi 1. Yes, and this is my B. Yes, so now let's fill up. So with which probability I will get 0? 1/2. Okay. What would be the resultant state? What? 0, 1 over square root of 2. Yes, I will write 1 over square root of 2 in front. 0, 1. This is fine answer. Yes, you can open brackets, but I mean, it's not necessary. Here there is a hint. How you can do this, just like there is a computation ability, how not to write it so long. Yes, but I suggest to practice this because here it's easier to make mistakes. You look onto the parts which contains 0 here, you summate square of the coefficients in front of them. This is 1/2 square plus 1/2 square. Yes, and this would be this probability. You write the sum which contains the first elements, and you normalize it to 1, to vector. But I don't write it because if I write it, you can consider this as a acting rule. Yes, and in a previous situation, yes, so the acting rule, yes, in the previous slide. So it is robust to misprints. Yes, there are too few things here. Yes, so and if I start to write exact formulas, it starts to be not robust to misprints. Yes, and you saw I made a misprint. Yes, for example, I made misprint here. Yes, and I mean this formula is robust, so yeah, there are a lot of self-checking inside here. Yes, and the exact formula is not robust. So I personally never recommend to use formulas which are not robust to misprints. Yes. Okay. Let us do 0.6. So don't worry, we have very few slides left. So yeah, would be not over time. Let's do 0.6. We measure the second CUDA. No, okay, no. Let us finish the 5, yes, because we did only half. Yes, probability 1/2, and the state 1 over square root of 2, 1, 0, minus 1. Yes, because it is here. Yes. 0.6. Yes, I will draw the the template, and you will think probability 0, state What? Yes. So let me a bit give a hint, yes? Because I want to have here the second qubit. So I want to represent it now in the form like this. Okay, it would be 1 over square. It would be A, yes, plus B psi 1, 1. Yes, so if it was a second part, second qubit, yes, I should consider all the states where the second qubit is 0. Yes. So I mean, this is the same if you change order, and but I mean, this is too hard to change orders, because especially here the change of the order doesn't change anything. Here change of the order change. I mean, it's not possible not to make a mistake. Yes, and people should not be punished for this. Yes, so but this way is much more robust. Yes. In that case, you will see 1 over square root of 2, 0, 0. Yes. So 0 plus 1, 0 plus 1 over square root of 2. Yes. Yes.
Yeah, and this is the side one.
Yes. 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 Thank you. Yes. You see, it's not so easy not to don't make mistakes. Yes. Minus 1, 1. Yes, so this is the way. Yes, and we get here 1/2, because this is here, this is here. And we get 1 over square root of 2, 0 plus 1, 1. Here 1/2, 1 over, oh, 0. No, 0, yes. And here we get 0 minus 1, 1. Yes?
Somehow the same.
No. This is the point. Yes? Because, no, if so, answer. Yes? A result, like, okay, this was planned as a homework to prove this. Yes? But in fact, if you measure 2 qubits and you first measure first qubit, and after this you measure second qubit, the total result in terms of probabilities, final results, would be the same. Yes, as if you measure first second qubit after this first. So the operations of measurement of 2 different qubits commutes.
Five. 0, 1, and then 6. Remember,
We also get 0 or 1 and some states. The states are different. Result. So I consider the result of measurement is 0, 1. I mean, this is the same distribution. Yes. But as a quantum system, they would be in a different states. So they're not equivalent. So they have the same distribution, but they're not equivalent. I mean, same as with random variables. It's possible. Yes, so that's. Yes. The same. Yes. And True, but I would on next slides explain what I mean under this in more detail. So, okay, let me finish with the examples and let me go. While in most of the computers, yes, what is implemented is actually the operation which I told. Quantum mechanics gives you a bit more freedom. So it's kind of restriction of physical device, not restriction of nature. Yes, this, what I will present now, is the restriction of nature. Yes, so it's not possible physically to create a measurement device more general than what I would present now. So measurement with respect to family of spaces, or sometimes it used abbreviation PVM, projection valued measurements. And here you need to have something as a parameter. And we consider, so our full space, which is C to the power 2 to the power n, yes, super high dimensional space, we represent it as a sum, not product. Sum, our usual, direct sum, yes, of linear spaces, such that they are pairwise orthogonal, and they have empty intersection. It is a subpart of the direct sum. Yes. So I have, it could be 2, it can be 3, it can be 10 of them. Yes. But they are pairwise orthogonal, and they give as a sum the whole space. Then for each state, psi k, I define, because they are pairwise orthogonal, I can define projections on each of the space. And let me calculate those projections. This will be also vectors. Yes, it's not a number. Yes, and I postulate that the measurement with respect to this system of linear spaces would be the following. This probability square of the norm of psi k, we will get a result k. So in our classical world, we get number k. Yes, and the state becomes psi k, but multiplied on a certain coefficient, so it would have a norm 1, because psi doesn't have norm 1. And what is it? Sorry. So what is important for mathematical correctness is that, okay, here I have 1 divided by something. What if this something is equal to 0? Yes. But it doesn't matter because it happens with 0 probability. Yes. So this is self-healing formula. Yes. Yes. So this is how it works. And this is my postulate. And what I can say, yes. First of all, 2 consequent measurements with the same thing will give you the same result, because after projection you are in a space Ek, so the next time all other projections will be zeros. The second thing, that just measuring 1 qubit is a special case of this story. Yes, if I would like to measure the first qubit, I consider 2 hyperplanes. One would be the linear space corresponding to vector 0, tensor product on all other qubits, and another is 1 tensor product to all other qubits. Yes, and sum of those 2 spaces will give the whole space. Those spaces they are orthogonal. Yes, so that's it works. Yeah, so this is a generalization. I think it might be possible that you never heard about such system measurement before, even that you have heard about quantum mechanics. Because in quantum mechanics, the same idea is used in a form of operator measurement. So let us consider self-adjoint operator, also energy operator, but now it is measurement operator. And in quantum mechanics, people quite often say measurement with respect to H. And this means the following. So H is a self-adjoint operator, so it has real eigenvalues, corresponding eigenspaces. Those eigenspaces are pairwise orthogonal, give the sum of, direct sum of them is the whole space. So we can consider the same construction, only that result which we get is now is not k, it's lambda k. It is in a certain sense better because what means k? Yes, and now it is certain physical object. Yes, so you will have some measurement devices. Yes, so that it's kind of it has a lambda k has a physical meaning instead of k. But in principle, it's the same because still there are finite number of them, and you kind of just encode. It's a question how you encode m different results. Yes, you can encode it from numbers from 1 to m, or you can encode it by m different real numbers. I mean, this is the same story. Yes. Yes. So okay. Before homework, yes, certain summary. I mean, today I think we already used some linear algebra. Yes, it's already. I mean, I cannot say that it is advanced, but I cannot say that it is basic. Yes, so we already kind of dive in mathematics. Yes, and of course, later we would consider operations in this linear space. So this is, I have to say, today I already showed philosophical concepts which would appear during the course. Yes, so you can consider that, okay, now I have a fundament, yes, and everything would be super advanced version of this fundament. Yes? So this is the building blocks. Yes, and so this is that I showed how parallelism works. So I showed which calculations I will do. In the measurement story, I worked a bit with eigenspaces, with projections. Yes, so this is what we will do from class to class. Yes, and for homework, yes. It's advanced homework, so don't expect that you can do this in Abessa, yeah, so that's, you need to think a bit. So 2 questions, yeah, so both of them are about the same. Consider 2 measurements, yes, and this could be, I would consider the qubits measurements and the measurements with respect to operators, yes, because I need to have a good answer. Yes, I don't know how good-looking answer in terms of projection value measurements, but I have a good answer in terms of operator. So we have, assume that we do measurement 1, we get some output. After this, we do measurement 2, and we get some output. And put in a state that phi 2 is the finest. And assume that we do in opposite direction. So we first do second measurement, and after this we do first measure. We also get some outputs. Now I will call it output 2, output 1, just to swap them as well. Yes, and we would have a final result. And I will say that they are equivalent if for any pair output 1, output 2, the probability is the same. And if output 1 and output 2 are the same, then the final result is also the same. Yes? This is the definition of equivalence. And basically, yes, they are undistinguishable in that case. Yes? Because if we got the same result, the quantum part, so the classical part is the same, and the quantum part is the same. Yes? So the question is when it is true that we can change the order. Yes, and so the first problem is measuring first qubit, measuring second qubit, and already told that yes, they would be equivalent, but I will ask you, say, to look for a two-qubit system and to calculate and realize that it is really like this. And second is if I consider measurement with respect to self-adjoint. Yes, H1 and H2. And this is now a question which I up to now leave open. I don't tell the answer. Yes, under which assumption they would be, you can swap the measurements. Yes, and I will, here I give a hint so that there are cases when you can, and there are cases when you cannot. Yeah, so, and I suggest, so there was a certain homework from previous class. I suggested the next class will start, with a short time that I hope that you will partially, not me, say yes, but I would stay here on the blackboard and write on a blackboard, but you would be the speakers. Yes, so I would be a pen. Yes. So okay. So more questions? So then, thank you very much. Yes, so today length of the lecture was exactly. Now those who want can stay on a Portuguese version. Stop. How I can stop?